Good morning, relativity friends. Um, I have an extremely polite but persistent viewer who is confused by the Riemann tensor. And I know why, because you don't have the right background. I'm sorry to be so blunt, but I'm too old to be polite. General relativity is based on Riemannian geometry. The language of Riemannian geometry is tensor calculus. Now, is this mathematically correct way to say this? I don't know. It's the way I understand it. You have to start here. If you don't have this background, this is not going to make any sense at all. Okay, having said that, let's try anyway. All right. But I highly recommend you seek out this course. All right. Here is the Riemannian. Its actual name is the Riemann-Christoffel curvature tensor. Everyone now just calls it the Riemann the tensor. But you can see why Christoffel got his name in here because that's all that it is. Now, like the tensor equation, you look for the free indices and you see what it is immediately. Here are 4 indexes that are free. That means they're going to be on either side of the equation and they're not going to be summed. That's the easiest way to explain it, right? So you see the sigma here, alpha, gamma, alpha, beta, beta, gamma. But then you get over here and you see a new index, okay? That's not here. If it's not here, then it's a summation index, right? So in the Riemannian geometry that we're going to do, Riemannian geometry is intrinsic. This means its properties determined solely by the Riemannian metric, and you know what that means. Defined on the manifold itself without relying on any external embedding in a larger space. So what we're going to do is imagine that you're walking around on the surface of a sphere and the radius is a constant. Right? Now what's that mean? That means we only have 2 variables. The variables in spherical the coordinates are r, theta, and phi, and we all know that. But if the radius is a constant, as it is when you're walking around on the surface of the Earth, right, then it's called the two-sphere of the problem, and only theta and phi are the only variables. All right. So here's the deal. This tensor has 4 free indexes, and we're working in 2 dimensions because the radius is a constant. That's important. So we need 2 to the 4, 16 Riemann tensors to go forward. Well, how do we do that? All right, let's let theta equal 1 and phi equal 2. So we can do this in numbers because it's easier. All right, so start with the contravariant, that's that guy, index the sigma equal to 1. All right, and find all the permutations of 1 and 2 when that is equal to 1. And you get this. There's 8 of them, right? So the position of where it is important, right? So just because there's a 2 and a 1, it doesn't, they have to be in that position because they're representing something that is in an equation. See? Where it is in this equation is important because you're either differentiating it or taking a product of it. So the position is important. That's the whole point of tensor calculus. Okay, so then you let the sigma equal 2 and you find the other ones. Okay, so we got 16 of these rascals. Now, what do you do now? All right, take the generalized equation and put back in all your 1s and 2s. All right, and here I picked one that I know is going to have a non-zero answer. All right, so you put in your thetas and phis and you get this. Now, how do we solve this? Okay, in the video number 5 of the playlist that you're watching, in video number 5, we found the basis vectors in spherical the coordinates. Okay, then in video 6, we found our metric tensor in spherical the coordinates. In video number 7, we found our Christoffel the symbols. Then they were only a 3 that are non-zero, okay? And so we put those back in this equation. And now I have to say something here. We found these based upon the fact that R is a constant, okay? R is a constant. We put these in, we crunch through the numbers, right? So you put everything in here that you found above. You do all of the math, grind, right? And you found one. Okay, so here is one example of the Riemann the tensor for the two-sphere the problem. Now, there's all kinds of the symmetry tricks that you can use to learn how not to do so many calculations. But any student, I did it myself. It's so painful, but it's how you learn. You just got to do reps. You got to do reps. It's like throwing a football. You got to do reps. So you just crunch through all 16 of those rascals, and you will find there's 4 non-zero ones. Okay. And you can immediately see the tricks I was talking about is that these two indexes, if swapped, gives you the negative of that one. These two indexes, if swapped, gives you the negative of that one. That's not important at this point. You should grind them out. Do every one of them. I know it's awful, but it really gets you used to doing indexes in tensor calculus, okay? Now, you've achieved this. You got 4 non-zero Riemann tensors, right? But you want to find the Ricci tensor because that's what's used in relativity. And this is something else you learn in tensor calculus is that if you want to take a 4-index tensor and contract it to a 2-index the tensor, the way you can do that is to change the middle index to the same letter. Okay? Don't worry about why that's true. It's true. So that makes that a summation index. So now we've only got 2 dimensions. So we only have to worry about theta and phi, right? And now we just put in our the rest of our information for u and v, all right? So we let, it's not u and v, it's mu and nu, I'm sorry. So we let them be theta, theta. Now just follow the rules. So you see here, this is the summation index. So we sum over theta and we sum over phi. And here's mu and nu. You see it? Mu and nu, mu and nu. Okay, we just found these above. They're right here, they are. So you get a 1 for that one. All right, let's do it again. So this time, mu is phi. So all we do is change that last index here and here to phi, phi. We don't have any of these. They're 0. We found out they're 0. All right, we do it again. So we're doing all the permutations of mu and nu with 2 dimensions. That's 4, right? So 2 squared is 4. So here we got phi and the theta. Once again, we don't have this one. We don't have this one. All right. Finally, we do phi, phi, and we get a hit because we had one of these. All right. So this is tensor contraction. All right. Where we're changing the middle index to the same letter, which makes it a summation index. Now we have 2 free indexes and we only got 2 dimensions, so we got to find 4 of these. Okay? Now what? Now we want to do a contract the Ricci tensor to find the Ricci scalar. Well, how do we do that? Because it doesn't have anything to change to. Well, this is one of the things the metric tensor does, is that it raises or lowers indices. And we want to get rid of both of them at the same time, so we just get a scalar. It has no indices. It's a tensor rank 0. So if we take the inverse metric tensor G mu nu with the Ricci, the tensor R mu nu, we have 2 summations here, see? U and V. So we have to sum over all of those. Like theta, 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 phi, theta. All of the permutations of theta and phi, we have to sum over all of them. And we know we know all of this because we have already done the calculations, right? So we plug in what we have, right? As an example, here's the two non-zero elements of the inverse metric, the tensor. Here's these two, and we crunch through the numbers, bada bing, and we get 2 over a squared. Okay, so we got the Ricci to scalars equal to 2 over a squared. Well, what does that mean? Well, this is that radius we held constant, right? So imagine this is, I don't know, the radius of a basketball, which means that this is going to be a large number, right? Because the radius of a basketball isn't very much. Well, what if this is a radius of the Earth? Well, then this is going to be a teeny number, very, very small number, right? So the basketball has more curvature than the Earth. That's why when we walk around on the planet, it seems flat to us, but it's not. It just seems flat because it's so big. Anyway, so that's what it means. I hope that helped. I'll see you later.